Friends, we continue with the study of voltage stability. We shall examine today the classification of voltage stability. We will also examine the techniques for voltage stability analysis. Under this voltage stability, we may have to study determination of shortest distance to instability, the continuation of power flow analysis and prevention of voltage collapse. Today, we will be addressing to the first two points pertaining to the voltage stability. In the previous lecture, I have discussed about the classification of voltage stability as large disturbance voltage stability and small disturbance voltage stability. This classification is similar to what is done for angle stability analysis. The large disturbance voltage stability is concerned with the system's ability to control voltages following large disturbances such as faults, loss of load or loss of generation. That is, whenever actually the disturbance is large in magnitude, right, then we call this as a large disturbance voltage stability problem. Now, when examining the large disturbance voltage stability of a system, one has to model and exclusively include the operation of some of the devices such as underload tape changers, generator field current limiters. Generally what happens is that these devices ULTC, they operate slowly. Now, suppose the voltage is low, voltage is at low level, then from that instant till the first step changing takes place, the time delay is quite large, right. And therefore, when you model the system dynamics or to capture the complete dynamics of the system, one has to include the dynamics of some of these devices like ULTCs and generator excitation current limiters and so on. In fact, the large disturbance stability can be studied by using non-linear time domain simulation which include proper modeling. Now, when we talk about proper modeling, it means it should include the modeling of all the devices. When we have discussed the angle stability, we give our thrust of modeling is the modeling of generator, modeling of excitation system, modeling of controls on the generator and excitation system, but we hardly can say concentrate on modeling of loads in that detail, right. But here when we talk about the voltage stability, one has to model the devices in more detail, because this voltage stability is relatively a slow phenomena and one has to capture the dynamics of the slow devices like say ULTCs, similarly the operation of thermostats, right. The small disturbance voltage stability, the definition of this small disturbance voltage stability is that small system voltage stability is concerned with a system's ability to control voltages, following small disturbances such as gradual changes in load. This form of stability can be effectively studied with steady state approaches that utilizes linearization of the system dynamic equations at a given point. That is, we make use of the linear model of the system for analyzing the small signal stability. Now, when we talk about voltage stability analysis, the analysis of voltage stability for a system state involves the examination of two aspects. Now, here when I say we want to analyze the voltage stability, it means we have to analyze the voltage stability at one particular operating condition. Suppose the system is operating at a one nominal condition or some condition, then we want to find out if a certain type of contingency occurs, how the system is going to behave, whether the system is going to remain stable or not. Like that. It means basically the analysis of voltage stability for a system state, means particular operating state, involves the examination of two aspects. One is proximity to voltage stability, or proximity to voltage not instability, voltage instability, proximity to voltage instability. That is how close we are, or how close is the system to voltage instability. This is what is the meaning, how close. That is the, suppose I am operating at a particular loading condition and the system becomes voltage unstable at a particular loading condition, critical load condition, then what is the distance between these two? That is called actually the margin also. Same approach is used actually in angle stability also, where when we are operating at a certain loading condition, right, then for a given condition, for a given contingency, we can find out what is the critical clearing time of the system, and we know the actual fault clearing time. So, that the difference between the critical clearing time and the actual fault clearing time, that gives the margin of stability, that is the margin. Suppose the critical clearing time for a given operating condition with a given contingency say comes out to be, let us say 0.2 second. If the actual fault clearing time is say 0.05 second, then we have a margin of 0.15 second. Similarly, we are also interested in knowing through the analysis that how close we are to voltage instability. That is, what is the distance to voltage stability. Then we are also interested in finding out what is the mechanism of voltage instability. The second aspect is to understand the mechanism of voltage instability. That means, how and why does instability occurs? What are the parameters, or what are the main reasons for the voltage instability? That is what we are interested in knowing through the analysis. Then what are the key factors contributing to voltage instability? What are the voltage weak areas in a complete system? There may be certain portion of the system which will be more prone to voltage instability. Then we can take corrective measures to make that system strong by injecting or by installing more of reactive power sources. What are the measures, or what measures are most effective in improving voltage stability? That is what I was mentioning, that the analysis should, when we do the voltage analysis, our objective is also to find out what are the effective measures that can be used for improving voltage stability. Now, when we perform the voltage stability analysis, first I will discuss the large disturbance voltage stability analysis. When you want to analyze this voltage stability of the system, then the most effective method is the simulation studies. That is, you have to do time domain simulation of the system, and when you do the time domain simulation, the requirement of modeling is important, and therefore, the models of power system elements that have significant impact on power system stability are, as I have discussed, the load characteristic, generator and their excitation controls, static wire systems and their controls, automatic generation control AGC. We generally we do not model the AGC for tangent stability analysis. However, since the voltage stability or voltage collapse phenomena is a slow phenomena, and therefore, the slow controls are also required to be modeled. The AGC is a slow control, automatic generation control, which actually is there to regulate the frequency tile line flows by regulating the generation of the system. Then we may also have to see the protection and controls, what protections are there in the system and what controls are to be modeled along with actually the complete system. So, that we have complete modeling of the controls, protection aspects, AGC, then the reactive power sources, loads, generators, everything has to be properly modeled. When I talk about loads, means again we have to model the regulating devices in the distribution system, we have to model the thermostats, right, and so on. When we talk about generators, we have to model the overexcitation limiters. Similarly, we have to model the overload limits of the generator and so on. Now, we go to the dynamic analysis. The general structure of the system model for voltage stability analysis is similar to tangent stability analysis. This is a very general statement that the mathematical model which we developed for dynamic analysis is similar to what we have for tangent stability analysis. Only difference is that we have some more additional detailed models of the system. The model comprising a set of first order differential equations may be expressed in the following general form. That is, when you look into the mathematical model of the system, we have a set of differential equations, a set of nonlinear differential equations, along with a set of nonlinear algebraic equations. And these two sets of equations have to be solved to get the complete time domain simulation. The basic equations of the system, differential equations, the set of first order differential equations are written as x dot equal to f of x v, where f is a general nonlinear function, x is the state vector and v is the bus voltage vector. This is the set of algebraic differential equations, the first order nonlinear differential equations. Then we have associated with this a set of nonlinear algebraic equations, which is written in the form I equal to y into v, where I is function of state vector and the bus voltage vector. Yn is actually the network admittance matrix and V is the bus matrix. This set of equations are same as the load flow equations which we come across, where we write down I bus is equal to y into V bus, right. Here also the same thing, only emphasis is here that yes, the current vector is function of the state variables as well as the voltage. Now, about this Yn, which is the network admittance matrix. Now, here when we model the system for stability analysis, voltage stability analysis, we do consider the tape changers or say under load tape changers. Therefore, when you have the under load tape changers operating as a function of time, then this Yn will also change at each time you have actually this change in the tape setting. that is Y n has to be modified. Therefore, whatsoever change that takes place actually in the system have to be accommodated in network admittance matrix. The initial operating condition is determined as XO VO, where initial state vector is XO and initial bus voltage vector is VO. We already specified that X is the state vector of the system, V is the bus voltage vector, I is the current injection vector, and Y n is network node admittance matrix, already studied. Now, to illustrate the voltage stability problem, we will consider this system. This system has been discussed by several researchers, and it is also discussed by Prabha Kundur in this book, Power System Stability and Control in chapter 14 on the voltage stability. This system has been discussed. The system comprises of generator 1, generator 2 and generator 3. There are 3 generators. Generator 1 is connected to this bus 7 through a transformer T1 and a transmission line. There are total 5 transmission lines in parallel. Generator G2 is connected through another transformer T2. Then there are 2 loads. One load is connected at bus 8 through a transformer T4 and another load is connected at bus 11 through a ULTC transformer at bus 11. Now, this system is considered for understanding the basic phenomena of voltage stability. Here we are talking about the large disturbance voltage stability, and the voltage stability is to be analyzed by time domain simulation, and therefore, all the generators have been modeled in detail, dynamics of the generators, dynamics of the excitation system, automatic voltage regulators and their limiters, they are all modeled in detail. Similarly, the loads at bus 8 and bus 11 are also modeled in detail. The tape changer at bus, the tape changer, that is under load tape changer on transformer T6 is such that the first tape change occurs in a time with a time delay of around 30 seconds. Then the second tape change will take place in 5 seconds, and this it has total of 16 plus minus 16 steps in tape changing, and the moment actually all the steps that it reaches the upper limit or lower limit, then the tape changer limits are reached. For this ULTC is also modeled. Now, with this complete modeling, the voltage stability analysis is carried out considering 3 different levels of loads, that is the loads at bus 8 and bus 11 total put together are classified as load level 1, load level 2, load level 3. Load level 1 is a light load, then 2 a further increased load, 3 is a further increased load. Now, the 3 load level conditions are. Now, here when the system is operated under normal conditions, a contingency occurs, and the contingency considered here is that out of this 5 transmission line, 1 line is tripped, right. Then the complete simulation has been carried out, and the response of voltage at bus 8, bus 11, bus 7 are recorded. In addition to the voltages at these places, for generator 3, the reactive power generated by the generator 3 is recorded, the field current of the generator 3 is recorded, and the voltage at the terminal of generator 3 is also recorded. Now, let us examine the responses which are obtained for this particular contingency. Now, here this diagram shows that this is the response for voltage at bus 11 for load level 1. Now, we can see here that initially the system is operating under normal conditions. The moment one line is tripped, the loading on other lines increases and it will cause a drop in voltage. Now, with this drop in voltage, the first thing which happens is that the generator AVRs will come into operation and they bring back the voltage to the original level. If you see actually the responses of voltages at all the 3 buses, that is bus 11, this is the response for voltage at bus 10, this is the level 1. Similarly, this is the response for voltage at bus 7. I told you that the responses for the voltages for these 3 buses 7, 10 and 7, 10 and 11 are recorded. Okay. This is 11, this is 7 and this is bus number 10. These are recorded, right. We could see actually that if there is loading is at this level, then the voltage is regulated to the initial value. Only for a short time there is a dip in voltage. However, if we examine now the response of the generator 3. For the generator 3, the 3 parameters were recorded. One is the field current in per unit. Now, for the load level 1, the field current, the moment there was a dip in voltage, the field current inside, you will find that when the voltage is regulated back to the regular value, the field current has risen, increased. But however, the field current remains below the limiting value, right, and therefore, there is no action of any other controller and the voltage is restored back to the initial value. Now, we can look at the reactive power output in MVR. The reactive power output of the generator 3 has increased from the initial value to this value, because the moment one line is taken out, additional lines are loaded and therefore, additional reactive power demand is posed on the system and the generator reactive power output has increased, but still this remains below the limiting condition of the generator. Things are fine. You can see that the generator terminal voltage in per unit, the generator terminal voltage is regulated to the desired value when the loading condition 1 is there and you have actually the particular contingency. With the same contingency occurring, if we are now at the load level 2, this is a higher level. In that case, what happens is that the moment one line is out, first the voltage dip take place, the generator will regulate the voltage, increase its excitation, bring it to the voltage is brought up to the initial value. Now, this happens and this remains at that level for a time equal to something like 180 seconds. Now, during this period, if you see the voltages, what happens at other buses, this is the voltage at bus 10, this is at the lower level than what it was earlier. Same thing is happening for the voltage at bus number 7. Now, when these lower level voltages are there, the immediate thing which happens is that the generator will try to bring the voltages and will try to generate more and more reactive power. so far the generator 3 is concerned, with this load level 2, you can see here the field current has increased to this level. Initially of course, it was at this level with load level 1. It has gone up, it remains there, but at this increased current level, since this field current is more than the rated value, what happens is that the overload or overcurrent field limiter is there, and this the field current will be ramped down. It will made to decrease from this level, therefore, this field current is made to come down. That is easily see, this is the level at 2 and it is brought down. It is brought down to the level, so that it is below the permissible limit. Now, during this period when the voltage is coming down, when the field current is brought down, voltage comes down. Now, during this period the OLTC or you can say underload tap changers will start coming into action, because the ULTC will try to restore the voltage at the load points. Now, when the ULTC tries to restore the voltage, right, you will find actually that the more of reactive power will flow on the lines. Where the voltage is restored, loads will draw more reactive power, and therefore, more reactive power flows, and with this more reactive power flowing on the line, you would find actually that the voltage will further drop. When voltage drops, ULTC will again try to boost it up. If you see these responses here, at this point somewhere at 180 seconds or so, the ULTC comes into operation, and at every step when it is trying to raise the voltage is coming down, and at this point it has reached the upper limit, that is the limiting condition of the tap changer has reached. So, that the voltage now settles down to a low level of the order of 0.95. Same thing happens for the voltages at other buses. You can see the voltage at bus 10, this is 11, at this particular point it started happening. This is the action of ULTC. Okay. Now, we can see what has happened to the reactive power output of the generator. The reactive power output has increased from this level, because this is the reactive power output at load level 2. The moment actually one line is out, it has increased. Now, this is now has gone beyond the limit. It remains there, and then it is stepped down or it is ramped down. It comes down like this. Okay. Now, let us look at what happens at load level 3. Now, at load level 3, if you just see here, this is the voltage at bus 11. At load level 3, the moment actually the fault occurs, or not fault, but the contingency takes place, line is taken out, the voltage dip takes place. This voltage dip is more here because the initial load is more, right. The first thing which happens is that the AVR will try to regulate the voltage and bring to the desired value. But in this case, what happens is that in a very short time, the AVR has touched its field excitation limit, and therefore, the AVR will no more regulate the voltage. Then immediately the ULTC comes into action and tries to regulate the voltage. But in every step when ULTC is trying to regulate the voltage, instead of voltage being regulated, it drops down, because every time the voltage is brought up, more reactive power demand is there, and that causes further voltage drop. So, you can see here actually the voltage drops to a very low value of the order of something like this 0.83 plus or 0.838 or so, 8.845 or so, something like that. You can just see the level drop down to this level. Similarly, if you see the voltage at bus 10 is happening like this, comes down, which is much less than 0.81. The voltage at bus 7 has gone down to this level, you can just see, that is 0.92 or so. If we examine the field current of the generator 3, then the moment this generator has come into action, the field current is increased to high level, then it is going to be ramped down and it comes to this level. Now, during this period the ULTC comes into action and the voltage, the reactive power demand, the reactive power demand, you easily see it goes up very high, then it is ramped down. Therefore, what we see here is actually that through this example, what I wanted to illustrate is that whenever some contingency occurs in the system gets overloaded. The first action is that the AVRs come into action, tries to bring the voltage to the desired value. However, in that process the field current may go beyond the required limit. Similarly, the reactive power generated by the generator may go up, so that the over excitation limiters will come into action and will ramp down the excitation from that higher value to the safe value. Similarly, reactive power will come down. When the voltages come down, the ULTCs will start functioning to restore the voltage, but in that process, instead of succeeding in restoring the voltage keeps on going down till the ULTC settle down to the limiting condition. This is the type of phenomena which has been recorded in this particular example. The next thing which we will discuss is the static analysis. So far the dynamic analysis is concerned, the dynamic analysis is very useful, but it is very time consuming. It requires actually the large number of time domain simulations, because for each operating condition, for each topology and for each type of contingency, the behavior of the system is going to be different. Therefore, one has to do large number of such studies. However, the dynamic study which is performed gives you clear picture about the voltage stability, causes what were the key factors which affected the voltage instability and so on. However, it does not give the information about how much my system is stable, how far I am from the voltage instability. That is, the distance from voltage instability is not can say determined through dynamic analysis. It gives the complete information, system is stable or not, this is how the system collapses, complete information you get it, but not this quantitative information that yes, what is the additional load which I can put on the system without losing voltage stability. The static analysis is simpler and gives some more insight into the system. The static analysis is possible only because the dynamics of the system is slow, and therefore, for when we perform the static analysis, we perform or we capture the snapshots over a certain time frame, and during this time frame we assume actually that the system is practically in the steady state condition, and therefore we can apply static analysis tools for determining the system stability. There are two important techniques which have been developed over the years. One is called VQ sensitivity analysis, another is called QV model analysis. I have already discussed actually the significance of the QV curves. We have also seen actually the importance of slope of these curves for stability, and therefore, this VQ sensitivity is on the similar lines, and we will study the VQ sensitivity first. To analyze this VQ sensitivity, we develop the steady state model of the system similar to what we do for load flow analysis using Newton-Raphson technique, where you can write down this as delta p delta q vector is equal to a Jacobian into error vector, see delta theta delta v. Now, here we will not call it as error vector or anything, we will say this is the deviation in voltage, this is the deviation in angle, this is the deviation in real power, this is deviation in reactive power. Therefore, this equation which is similar to our load flow equation is used for performing the VQ sensitivity analysis. Here this delta p is the incremental change in bus real power, delta q is the incremental change in bus reactive power, delta theta is the incremental change in bus voltage angle, and delta v is the incremental change in bus voltage magnitude. Now, here to obtain this VQ sensitivity, what we do is we assume the deviation in real power at the bus equal to 0, that is we make delta p 0. Now, once we make delta p 0, then by matrix simplification we can eliminate this term delta theta, that is you can write down the expression for delta q in terms of delta v only. Now, this approach is similar to the bus elimination technique which we make use of in the fault analysis. When you develop the Z bus matrix and so on, the similar approach is required. That is, we can write down here delta q in terms of delta v and this matrix ZR. This matrix ZR is obtained in terms of the 4 elements of the Jacobian matrix ZQV, ZQ theta, ZP theta, ZPV. I will advise these people to derive this expression and satisfy that we can obtain the reduced Jacobian matrix JR as JQV minus JQ theta, JP theta inverse JPV. Now, using this equation, we can write down delta V as JR inverse delta Q. It means this equation relates the incremental change in bus voltages to incremental change in bus reactive power through this matrix JR inverse. This JR inverse is a full matrix, right, and therefore, I can find out the sensitivity of ith voltage or sensitivity of voltage at ith bus with the reactive power change or incremental change in reactive power at ith bus in terms of diagonal elements of JR inverse. Because JR inverse is a full matrix, but I am interested in finding out the let us say delta Vi versus say delta Vq, not delta Vq, delta Qi, that is incremental change in voltage at bus I with incremental change in reactive power at ith bus. This ratio is nothing but the diagonal ith diagonal element of the JR inverse, right, and thus I can find out the VQ sensitivity, right. Now, here our requirement is for this VQ sensitivity, basically the QV curves which we have generated from the QV curves one can find out the VQ sensitivity, but however, to generate those VQ curves is a very cumbersome process. But now we get the information about this, the voltage VQ sensitivity by through this matrix JR inverse straight away. Now, so the system is stable when this sensitivity is positive, and in case it is low, it is more stable, in the sense that in case suppose this quantity is very large, that is, if the sensitivity is very large, the meaning of this is a small incremental change in reactive power at bus I will make a large change in voltage at bus I, that will lead to instability. Therefore, requirement is it should be positive and small for the stability. In case this quantity is negative, that indicates that system is unstable. Now, generally instead of taking the inverse of this matrix, that is JR inverse, one can find out this information right from this matrix itself. Now, this is delta Q JR delta V. Therefore, we get the information through the elements of JR, how this change in delta Q or change in Q is related to change in V, or incremental change in Q is related to incremental change in V. But whichever way you determine, one can find out the VQ sensitivity, and using this VQ sensitivity one can make out the voltage instability or find out voltage stability. Another technique which has been developed is called QV model analysis. Now, in this QV model analysis, we make use of the information about the eigenvalues and eigenvectors of the JR matrix. That is, this matrix JR, which is the reduced Jacobian matrix. This JR is used to further obtain the information about the voltage instability using QV model analysis. The approach is very simple. This matrix JR can be written as matrix zeta is a matrix, into lambda is also a matrix, into eta. This zeta is the right eigenvector matrix of JR. That is, what is doing, that take this matrix JR, then find out the eigenvalues, then for each eigenvalue you find out the eigenvector, right eigenvector. Then since this matrix will have n eigenvalues, if it is n by n matrix, then there will be n eigenvectors. Therefore, you obtain this right eigenvector matrix making use of n eigenvectors. That is, these eigenvectors will become the columns of this eta matrix, this zeta matrix. Okay. This is the, similarly this eta is the left eigenvector matrix of JR. One knows about what we mean by the left eigenvector and right eigenvector. This lambda is the diagonal eigenvalue matrix of JR. That is, JR suppose has n eigenvalues, then this lambda is a diagonal matrix. The elements on the diagonal are eigenvalues of the matrix JR. Now, at this point I want to mention here that in case you neglect the resistance of the system network and the system is symmetrical, then these eigenvalues come out to be real. Generally, you will find actually that we have a real complex conjugate eigenvalues in the system, but for this particular system, power system, where if you, the resistances are negligible as compared to the reactance of the network system. If you neglect the resistance, right, and you will if we do not consider again the tape changers position, because the tape changers will make this Y matrix or bus admittance matrix unsymmetrical like that. But however, their effect is small. Now, this is a real, this eigenvalues are real, and therefore, actually the diagonal eigenvalue matrix of ZR is written as lambda. Now, our interest is again to find out the how incremental change in Q is related to the incremental change in V. So, that we make use of this expression. Now, here JR inverse can be written as eta lambda inverse, I am saying zeta lambda inverse into eta. Now, this is possible because this relationship exists between this right eigenvector matrix and left eigenvector matrix. That is, the zeta inverse is equal to eta, and because of this relationship, that is inverse of JR can be written as zeta lambda inverse into eta. One can verify this relationship. Now, you substitute the value of JR inverse in our original equation, that is delta V is equal to JR inverse delta Q. Therefore, this JR inverse I am substituting this expression. So, when I substitute for JR inverse zeta lambda inverse eta, we get this relationship delta V equal to zeta lambda inverse eta into delta Q. This is a very important relationship. How it is important? Let us just look into it. We can further simplify this. We multiply both the sides of this equation by eta. You multiply both sides by eta, then you will get eta delta V equal to lambda inverse eta delta Q. Why? Because eta into zeta inverse is one identity matrix, because that is, you can say eta into zeta. This product is an identity matrix, right. So, that we have this relationship which I have shown here, that eta into delta V is equal to lambda inverse eta into delta Q. That is, when you talk about the QV, model QV analysis, this is the most important expression. Now, in this expression we see here actually what is eta? Eta is actually the left eigenvector matrix, is a matrix. Suppose that when this matrix is multiplied with this vector, we will get a vector. This vector we denote as small v, and this vector will be called actually the vector of model voltage variations. This delta V is incremental change in voltage, but this product is called model voltage variations. In fact, actually here this V is a vector, right, and this vector contains the information or the of all modes in the system. All the modes are represented, right. Q is represented as eta into delta Q, which is called as model reactive power variations. That is, instead of having the vector of reactive powers, incremental change in reactive powers, now we have got here model voltage variations. This is a vector of model voltage variations. This is a model reactive power variations, and therefore, we get this information here. Very interesting expression. Now, since this lambda is a diagonal matrix where diagonal elements are the eigenvalues of JR, these are the eigenvalues of JR, and therefore, if I write down here the ith component of the model voltage variation, then this ith component can be written as 1 by lambda I into Q I, where Q I is the ith reactive power, ith model reactive power. Okay. Now, what we see here is that this V I is inversely proportional to lambda I, right. In the sense, actually here we get a relationship which shows the relation of the model voltage vector, model voltage of ith bus in terms of model reactive power change at ith bus in terms of eigenvalue of the GR matrix, right. Now, here suppose lambda I is positive. What does it show? Positive lambda I shows that the model voltage variation vector is along with the model reactive power variation, in the sense that when the reactive power varies in a positive direction, then the model vector will also vary in positive direction, and that shows that system is stable. But suppose if lambda I is 0, that is a case of instability, because that means a very small, because this becomes V I becomes infinite when Q I is small, right. Therefore, if lambda I is 0, it is unstable, while if lambda I is positive, is stable, and in case lambda is small positive, it is more stable. If large positive, it means lambda I is 0 is unstable, lambda is positive is stable, right, and if lambda is negative, system is unstable. Now, here I will just give you the relationship between VQ sensitivity and lambda eigenvalue. The relationship is like this: delta Vk, one can establish this, delta Vk divided by delta Qk is equal to summation over I zeta Ki eta Ik divided by lambda I. In fact, this gives you a relationship between the two approaches. One approach is based upon VQ sensitivity, another approach is based upon the eigenvalue, right. The model analysis is based upon the eigenvalue, and they have told you the eigenvalue is positive. You can see that this VQ sensitivity is inversely proportional to lambda I, right. Now, one simple example we can consider here. The example is that you have a strong system, infinite bus system, which is supplying a load through a transmission line, to a load through a transformer. At this bus, you have a reactive power source where you are injecting the reactive power Qi. And this becomes a simple system. Therefore, this voltage is fixed V1 is equal to 1 per unit, its phase angle is 0, and only quantity which is varying is V2, right. Now, this for this simple problem which is solved in example 3 of the example 14.3 in the book Power System Stability and Control by Prabha Kundur. I will give the results. What has been done is that for a particular load is about 1500 megawatt, the VQ sensitivity analysis and QV model analysis have been applied. Now, in this particular case, the JR becomes simply a 1 by 1 matrix. JR becomes 1 by 1 matrix, and therefore, the problem becomes a simpler one. However, actually the results are very interesting. The results are shown here. The studies are carried out for different values of reactive power injected at bus 2. Suppose it is 500 megawatt MVR is 400, 306 and 305.9, just to show the difference if we go from 306 to 305.9. For this, the voltage is computed V2. In fact, for each value of the injected reactive power, there are two solutions for the voltages. One is 1.024, another is 0.671, the lower one. There are two solutions always, because it is a nose curve. The phase angle is computed. Yeah. Now, you can see here in this diagram, this is lambda I, not very clearly shown here. This is lambda and this is dV by dQ, right. The lambda for this 500 MVR injected is 17.03 and the corresponding dV by dQ is small of the order of 0.059. Although, when you talk about the other part, other solution, lower solution, system is unstable because lambda is negative and dV by dQ is also negative. Right. Now, through this example what we see here is, as the injected reactive power decreases from 500 to 306, there is a drastic change in the value of lambda, there is 17 to 0.52. Larger the value of lambda, right, system is more stable. It is similar to damping ratio in a small signal stability analysis, right. Now, this 306 and 305.6, if you see here, the lambda has changed from 0.52 to 0.02 by a small change in Q by 0.1 MVR, right, like this. Now, with this, let me sum up what we have discussed today. We have discussed the two important aspects. One is the classification of voltage stability phenomena. Then we have discussed the techniques for analyzing the voltage stability of the system. I have illustrated the application of small signal stability analysis through an example, and we have seen that how actually the system functions and how the system voltage collapses. Then we have studied the two static voltage stability analysis tools. One is the VQ sensitivity, another is the model QV approach, and a simple example we have illustrated the application of these techniques to a simple system.